Hello, can you hear me?
Hi guys.
Hi, how are you doing?
I'm doing good. How about you?
Yeah, doing all right.
Great.
Looking forward to the talks.
Nice to meet you, Joseph.
Yeah.
Yeah.
Hi, nice to meet you guys. Sorry, I didn't talk at first because I wasn't sure if it was like broadcasting or something. I don't know how this works.
I think, neither do I. Well, I think we're being recorded at the moment, but I'm not sure if the attendees are in the room yet. I had the same response as you had. I was just like waiting. Yeah, there we go. Hello.
Hello. Sorry, I'm just trying to stream it onto Facebook. So yeah, this is my first time doing that. So I'll be like a minute or two. Yeah.
No problem. In the meantime, shall I start sharing my slides?
So I'm going to give like a small introduction because it's the first talk for the term. So we'll just wait like five minutes and let everyone join, and then we'll get going. Yeah.
Sounds good.
Yeah. So I'll be sorry. I won't be long. I'll be like a few minutes.
Oh.
Feel free to like chat.
Cool. Yeah. So what have you guys been up to?
That's the same really as everyone, I guess. So do you guys know each other?
Yes, we're in the same group.
Ah, whose group you?
Flecko Federals.
Ah, okay. Mm-hmm. On like quantum information computing side of things or physics?
Yeah, so I think everyone in Flecko's group has a specific topic of interest, and I work on quantum information, kind of foundations of quantum physics stuff. Mm-hmm. And but yeah, everyone has their kind of niche within the group. It's quite nice. See, we're streaming now on Facebook.
Can't hear me.
Oh, is it working?
Oh, yeah, no.
It says so, yeah.
Yes,
okay,
it's live.
Cool. I got an error message saying unable to, what does it say? It said, yeah, unable to broadcast, but if it looks like it's live, then that's great. Okay, cool. So let's wait a few more minutes just to let more people join, and then we'll get started. Yeah.
Cool.
Oh yeah, I can see the attendees. This is my first time hosting a Zoom webinar, so it's a little bit different to the usual format.
Oh, I see. You got panelists.
Yeah, I see we have 4 attendees.
Mm-hmm.
But we can't see the Facebook attendees, right? They're like a separate thing.
Yeah, no, it doesn't like register as an attendee on Facebook.
Yeah, so maybe there's millions of people watching us right now on Facebook.
There's definitely millions of people watching.
No fracking.
It says 7 people are watching on Facebook, maybe.
Oh, okay, yeah, you can see. Nice.
Ah, can you?
That
How do you see that?
That includes me, because I just opened it up.
Quantum information. I almost shared it to my own Facebook page initially.
good, you know, the more
Which
viewers.
would have, well, yeah, I mean, Amy Solid's live, but yeah, that would have been, I would have got, I think, yeah, a few more people interested. Yeah, let's wait until like maybe 7 or 8 minutes past, and then we can start.
I saw you had quite a nice lineup of speakers this term. Simon Sanders is going to give a talk, right?
Yes, yeah.
That should be fun.
Yeah, I think it's sort of split between mostly foundations and then a bit of like NISC type stuff. So we have like Campbell next week, who's currently working at AWS, which is cool. Yeah. And then after that, it's sort of like foundational stuff for a bit. And then Ross Duncan actually just agreed to give a talk, which is nice, on some like ZX calculus stuff. So it's cool because we have, I think, yeah, sort of some kind of split. It would have been nice to get some more kind of condensed matter type stuff, but there's always next term for that, so that's okay.
Nice.
How is everyone holding up in the second year of lockdown?
Yeah, doing all right. How about you guys?
Yeah, making it through. Maybe we'll get to go back to the physics department sometime soon.
Yeah.
Maybe everything will continue to be virtual for.
Yeah. I mean, I don't mind it. I think I wouldn't mind a day or two a week where I got to go to the office.
Mm-hmm. Right, okay, I reckon we just start then. So I'll give a bit of an introduction. So yeah, I guess because this is the first talk, I'm just going to speak a bit about the society. Basically just saying that we do have a great program of speakers lined up, which you can find on the Facebook page or the website. I think the website's been updated already. Yeah, if there's someone you'd like to see, just like drop us a message and we'll try get them to speak. And then I'd also like to advertise for a new committee position. So this is kind of essentially a publicity officer, but you will be responsible for writing the blog posts and the weekly newsletter and all of that. So if you're interested in quantum information and you also have a background in writing, or maybe you don't and you're just interested in that, then get in touch. And then yeah, we're also organising some other events with other universities. So we're going to have some kind of collaboration with Cambridge, Imperial and Berkeley as well, which would be really great. We don't know what that is going to look like yet, but we're thinking sort of like a small conference. Okay, so without further ado, let's get started. So we'll start with Sam, who's our first talker. So he's going to be speaking about Everettian states, specifically in the Heisenberg picture, and if I'm not mistaken, how this relates to locality. So yeah, but please share your screen and get started.
Great, will do. It says host disabled participant screen sharing.
Interesting.
So if you go, I think if you go down, there should be a button next to your screen sharing, which if you press it, it gives you a bunch of options. One of them is
I see.
Allow participants screen sharing.
Okay, so perfect. It should work now then.
Great. Yeah, there we go. Okay, so if I'm correct, you should now be able to see my screen, or at least my presentation. Great, yeah, so I'm Sam Kuipers. I'm a physics student, DPhil student at Oxford University, and I will be presenting about Everettian relative states in the Heisenberg picture, which is some work I did with David Deutsch. And just to give you a brief overview of what the talk will be like, I'll first present Everett's work in the Schrödinger picture and kind of explain how his construction, like what problems his construction solves, and after which I'll kind of give a brief criticism of it, and then motivate why we should want to formulate the construction in the Heisenberg picture. And then from that, I'll give you the construction that Deutsch and I created. I'll just briefly. Okay, so to just get straight into it, the state of the discussion before Everett came along was something like this. We thought that dynamical evolution in all quantum systems is unitary at all times, except according to most traditional interpretations of quantum theory during measurements. And it's this problem, it's this exception that Everett got rid of. And the way in which he did this is by treating not just the systems being measured as being described by quantum theory, but he used quantum theory as a universal physical theory that applies also to measuring instruments. So you might consider a kind of model universe consisting of a qubit in a superposition of its eigenstates 1 and -1, and a measuring instrument M initially in the state shown here, M, and it's a separable state. That's an important aspect of the model. And now you can describe how this measuring instrument would measure the superposition of eigenstates of the qubit. Namely, it would evolve into an entangled state where the states M1 and M-1 of the measure represent that these are the states of the measuring instrument having recorded a 1 or a -1. And there's some properties of the measuring model that are important. For example, you can see that there's no cross term, so there's no state of the measuring device that says M1 when it has in fact measured a -1. And also we're assuming that these states of the measure are orthogonal. In other words, they're exactly distinguishable from one another. And as you can see, there's now two states of the measuring instrument, one of which recorded a 1 and one of which recorded a -1, and they both exist together in the same universal state vector. They both exist simultaneously. And it is in this sense that every possible measurement outcome gets realized in Everett's many worlds interpretation. And the so-called relative states are the individual histories of the measure. So for example, the relative state M1, which is the state of the measuring device relative to having measured value 1 of the qubit, is typically assumed to then evolve independently from the other state or from the other relative state M-1. And so this is a very brief overview of kind of Everett's relative state construction in the Schrödinger picture. And the reason why Deutsch and I thought this was not a complete solution is because the Schrödinger picture itself is not a local formalism of quantum mechanics. And in other words, Everett's formalism cannot be local because it is formulated in the Schrödinger picture. So why is the Schrödinger picture non-local? And in what sense is it non-local? So I use the sense of Einstein's criterion. In other words, something is said to be local if the real factual situation of a system S1 is independent of what is done to a system S2, which is spatially separated from the former. And quantum theory in the Schrödinger picture is non-local because, for example, you can apply a phase shift gate to a state of qubits in a Bell state. And you can apply that gate to one qubit. So for example, the qubit on the left, in which case the gate is represented by the Pauli matrix Z, and resulting in this relative phase. But none of the information in the state actually records where this operation was performed on. So the Schrödinger state doesn't distinguish between the operation being performed on the left qubit or on the right qubit. In other words, this is symmetry. And this is why Einstein's criterion is violated, because the state of the system does not record which parts of it remain unchanged and which parts of it remain or are changed by an individual operation. And that's because there's no way of describing subsystems in the Schrödinger picture. There's only the possibility of describing the entire system at once. In other words, the Schrödinger picture is not a local formalism of quantum theory, but quantum theory is a local theory because it also allows for a local formalism, and that is the Heisenberg picture. And I think this is a good motivation for wanting to have a formulation of average relative state construction in the Heisenberg picture, because the Heisenberg picture is in some sense more fundamental than the Schrödinger picture is. So Deutsch and I constructed average relative states in the Heisenberg picture, and for this we used a quantum computational network. The reason why we use the quantum computational network is because it ensures the generality of our result, not because such networks are the most universal quantum system. For example, they consist of qubits that interact during fixed periods, but they do have the unique property that they can simulate with arbitrary accuracy any other physical system. And it's this property that will ensure that our construction is in fact completely general. So in contrast to the formalism of the Schrödinger picture, the Heisenberg picture consists of evolving Q number observables and a fixed state vector. And specifically, we'll now be talking about an n-qubit network. And in an n-qubit network, each qubit is represented by a triple of Q number descriptors, which have the algebraic constraint that the descriptors of an individual qubit adhere to the Pauli algebra, which is the first line below. And also the descriptors of separate qubits commute with one another. Now, a simple way of thinking about this is by using matrix representations. And an n-qubit network, you can use 2n by 2n matrices, Hermitian matrices, to represent the descriptors. And perhaps the simplest example of this is when you have a single qubit network, in which case the initial matrix representation can be assumed to be equal to the Pauli matrices, which of course adhere to the Pauli algebra. And you can generalize that initial matrix representation to networks of n qubits by using products or tensor products of identity operators. And these tensor products ensure that the qubits, that the qubit descriptors of different qubits commute with one another, but that the qubits individually in isolation adhere to the Pauli algebra. Now, these descriptors represent the network at any particular time, but we also want to describe how the network evolves. And in a quantum computational network, it's convenient and conventional to assume that a gate acts during exactly 1 unit of time. And a general gate is represented by a unitary. A unitary, for example, of a gate G is represented by the unitary UG, which is a function of the descriptors of the network. And each qubit, so for example, the 8th qubit of the network, is evolved forward 1 unit of time by conjugating the descriptors at time t with this unitary. So that's the equation here below. And an important property of this kind of evolution is that it preserves all of the algebraic properties of the descriptors. The matrix representation, in fact, changes, as I'll show in the next slide. But the algebra of each qubit descriptor remains unchanged. So for example, if you take the product of two descriptors at time t+1, then you can express that product in terms of the descriptors at time t. And then with some clever mathematics, you can notice that, for example, the unitaries, the product of unitaries in the middle cancels out because they're unitaries. Then you can insert the algebra at time t, and then evolve that algebra at time t forward to obtain that the qubit descriptors at t+1 also adhere to the same Pauli algebra. And likewise, you can show that when descriptors commute at time t, they also commute at time t+1 and any other time because of the unitary evolution. To kind of get a bit of a deeper understanding of how this kind of description works, it's nice to think of the example of the NOT gate performed on qubit A, which has as its characteristic expression that the unitary for this gate is equivalent to the X component of qubit A. And the effect of that unitary on the network can nicely be expressed algebraically, which I've done below. So you can see that the descriptors of QA at time t+1 are this rotation of the descriptors at time t. And in particular, you can see that the effect of the NOT gate really does what a NOT gate does, because it toggles the eigenvalues of the Z component. So the Z component at time t+1 is equal to the Z component at the time t times a minus sign. So that kind of corroborates that this gate that I'm claiming is the NOT gate is in fact the NOT gate. Now, so to prove this claim that I made earlier, that the Heisenberg picture is in fact a local description in Einstein's sense. So in the sense that if you have subsystems, then you can perform individual operations on those subsystems without them affecting other operations. You might consider a single qubit operation F, which you perform in qubit A. And because this is a single qubit operation, the unitary UF that implements this operation is only a function of the descriptors QA. So the effect of this unitary on some general qubit in the network that is not QA will be to leave that qubit completely unchanged, because separate descriptors in the network commute with one another, and therefore its effect cancels out. Meaning that if you perform a single qubit operation on qubit A, it is really only qubit A that you affect with this. No other qubit in the network changes whatsoever at the level of their descriptors. And it is in this sense that the Heisenberg picture adheres to Einstein's criterion of locality. We can perform individual operations on single qubits or subnetworks of qubits without those operations affecting anything else in the network. So the Heisenberg picture is, I claim, local, as proven by Deutsch and Hayden, I should say. This is all work done by Deutsch and Hayden. And it's also a complete description in the sense that if you're given the n triples of descriptors, then you know the full state of the network. If you're given the descriptors and the Heisenberg state, which I'll come to in the following slides, then you can say compute any expectation value or any probability that a measurement will occur one way or another. And so they fully specify the network, the state of the network. Now, to get to the Heisenberg state, I want to introduce some brief notation. I want to say that I want to denote the expectation values of observables as follows. And I also have a terminology by which I say that a descriptor or an observable is sharp if the Heisenberg state is an eigenstate of that observable. In other words, if the square of the expectation value is equivalent to the expectation value of the square of that observable. And the Heisenberg state in our construction is kind of lesser importance than it usually is, because we fix it to be a standard constant. We say that the Heisenberg state is such that all of the Z components of the descriptors are, of all qubit descriptors, are initially, sorry, I should rephrase it, all the Z components of all the qubits in the network are initially sharp with value 1, which uniquely specifies the Heisenberg state up to an irrelevant phase factor. And this means that no information about the actual state of the network is contained in the Heisenberg state. The Heisenberg state is that's a misnomer. It doesn't contain any information about what the network has done or is up to, because it's a standard fixed constant. And now that I have kind of provided this overview of the Heisenberg picture and of Everett's construction in the Schrödinger picture, I want to combine these two and give an explanation of how to write down the relative states for the descriptors in the Heisenberg picture. And this is the original research. The way that Deutsch and I went about this is by considering a 2-qubit network where one qubit, QM, represents an idealized measure and is programmed to measure the Z observable of another qubit, QS. And we take the initial qubit descriptors to be represented by the descriptors below. I also dropped the time labels t equals 0 just so that it's a little bit easier to see what's going on. It makes notation slightly better. And also just a reminder that, as I said before, the z components of both qubits are sharp at time t equals 0. Now, because we're mainly interested in measurements of non-sharp observables, and because the z component is initially sharp, we apply a Hadamard gate to the qubit QS, which in the Heisenberg picture has the effect of exchanging the z and x components and giving a minus sign to the y component. And this ensures that the z component of the qubit that will be measured is in fact non-sharp. It is in a superposition, as you would say in the Schrödinger picture. And also you can see that this feature, which I explained about the Heisenberg picture, that single qubit rotations only affect the qubits that they apply to and no other qubits, is satisfied by the Hadamard gate, because qubit m has remained completely unchanged by this operation. Now, during the next period, the qubit QM performs this idealized measurement of the z observable of QS, and that idealized measurement is implemented by the C0 gate, which, interestingly enough, was first named the perfect measurement gate by Deutsch, but it's typically called the C0 gate. The effect of that gate is to perform a NOT operation on the target qubit, which in this case is QM, if the z component of the control has value -1, and the gate does nothing to the target if the control has a z component with value 1. And you can see that this is in fact the effect of the gate, because I've used these projection operators here. So the projection, so P1 represents a projection operator projecting onto the eigenvalue 1 of QSZ, and P-1 is the projection operator that projects onto the eigenvalue -1. And you can see that the projection operator P-1 has this product with the NOT gate, meaning that when QZ has value -1, the NOT gate is applied to QM as desired, and nothing happens to QM otherwise. So if you use this gate and represent in a straightforward way what happened to the qubits, then there's a rather opaque expression that you get with these products of descriptors at previous times. And this is very strange in one sense, because in the Schrödinger picture, the effect is quite straightforward. You end up in a Bell state, and the relative states of this measurement would then easily be obtained, because you can see that they would simply be the states 1, 1, that would be one relative state, and the other relative state would be the state -1, -1, and together they make up the complete Bell state. So this is a problem, but it can be resolved by expressing the effect of the C0 gate in an alternative but equivalent manner. So you can see that the effect of the C0 gate is to perform a NOT operation on QM, as I said previously, if QSZ has value -1, which is what you can see at the right-hand side of this sum. And then it does nothing to QM if QSZ is sharp with value 1. And these must be the relative states of the measurement. So the relative states must be the qubit descriptors QM multiplied by these two projection operators, because they are the different instances of the qubit. So that's what I call the relative states. And to abbreviate the notation, I write them as QM1, which is the descriptors QM multiplied by this projection operator. And likewise for the value -1. There's an interesting feature of these, what we call the relative descriptors, which is that they have their own algebra. So they no longer adhere to the algebra of the absolute descriptors, of the original descriptors, in some sense, because their squares, the squares of the components are equal to these projection operators, which you can derive from the definition. In other words, because the original components were multiplied by this projection operator, and because initially the square of a component is the identity, the square of a component must now be equal to a projection operator. And likewise, multiplying these projection operators with the qubit components leaves the qubit components completely unchanged. So these projection operators are like the identity operator within a universe or within a relative state. And we can also see that if you write down the algebra of these relative descriptors in terms of their respective unit observables, relative unit observables, they again adhere to the Pauli algebra. And this shows that these relative states, these Everettian universes, must also be quantum systems. They're systems described by Q-number descriptors, which have a unique algebra, and in fact, the same algebra as the original qubits did. So with that, I'll conclude the talk by saying that these, by formulating the Everett's construction in the Heisenberg picture, you find an entirely local formalism in which the separate Everettian universes are spatially bounded and are also just fully quantum mechanical because they have these Q-number descriptors. And with that, thanks so much for listening. And if there's any questions, please ask.
Thanks, Sam. Right, so we have one question, which I'll read out. So Matthias says, is there a number of systems from which you could take the qubit descriptors and then in brackets the QIs that would allow them to remain the same as you consider even larger systems? And then in brackets, instead of having to replace 2x2 matrices with 4x4 and 8x8 as you look at a particular qubit in the context of even larger systems?
So I think that is a question about the matrix representation. And if I understand correctly, what Matthias is saying is that the matrix representation scales for larger and larger systems. If that's what he means to the question, then I would say the matrix representation isn't really fundamental. It's the algebra of the descriptors, that is. So if you have two separate qubits and you combine them into a composite system, then you must have rules for what multiplying these descriptors of the separate subsystems is like. And as it turns out, they must commute with one another. And that means that the matrix representation must be larger than it is for the qubits individually. If you drop some of those assumptions, then you might not need to use matrices that scale the way Matthias just described with this question. And that's kind of an interesting open question of what that would be like.
Right, okay, thank you. So are these, I'll sort of follow through with something. Are these algebras then somehow more fundamental in this Heisenberg picture than in the Schrödinger picture? Is there more emphasis on it?
Yeah, I think so. And I think in the Schrödinger picture, it's very easy to forget about the algebra of descriptors or observables, depending on what kind of terminology you prefer. But the fact is that any two Hilbert spaces of the same size have exactly the same structure. There's an isomorphism or something between them. And it's the algebra that gives these spaces more structure. It's the algebra is really fundamental. And you define, in some sense, you define the Hilbert space as a consequence of the algebra of the observables, not the other way around.
Right, okay. So emphasis on what is observed.
Yes. Well, it's in some sense, it's emphasis on the observables, but the observables have many properties that are not directly observable. They're much, in some sense, they're much larger than the state vector is. A colleague of mine has written in the paper about how much information you need to actually describe the descriptors, and it's quite a lot in some sense. But yeah, it's definitely an emphasis on the observables.
Okay. Great, thank you so much for that.
Yeah, thanks for having me.
So,
I'll stop screen sharing now.
Great, yeah. So we can move on to our second speaker, who's Joseph Tyndall, and he's going to be talking about, if I remember correctly, open quantum systems and how basically having heating is not always detrimental to the system. So yes, if you just go ahead and share your screen, Joseph, and then yeah.
Share it now. Can you see that? All right, is that okay?
Yeah.
Okay, brilliant. Okay, yeah, so thank you for inviting me, Amy. And so, yeah, I'm a student here at the University of Oxford. I've just submitted my thesis, and so I'm going to give a sort of quick, broad talk on basically what's contained within that thesis. And so the main result of my thesis, which is effectively a statement on the fact that the identity matrix isn't quite as simple or as boring as we think it is in the context of many-body quantum systems, and specifically strongly correlated quantum systems. So as a kind of outline of the talk I'm going to give, I'm going to talk about the identity matrix, you know, what it means in mathematics, what it means in a quantum mechanical setting, and then I'm going to talk about it in the context of my research and why it's important and more interesting than it seems. So to start with, the identity matrix, I'm sure we're all pretty familiar with what it is. It's probably the first matrix you're introduced to when you're taught about matrices. It's just a square matrix with ones on the diagonal and zeros everywhere else. And whilst, you know, it's incredibly simple, it's a pretty fundamental matrix because, you know, it's the identity element. It tells you that if you take any other matrix and you multiply it from the left or the right with the identity matrix, you get it back, same matrix back. Sort of the defining property of the identity matrix. And it also serves to define the matrix inverse, right? If you can find a matrix such that when you multiply it with another matrix, you get the identity matrix, then you found its inverse. So it's a pretty important matrix, but it's very simple, right? All the eigenvalues are 1, all its eigenvectors are just unit vectors, and it probably doesn't feel like there's really much more to say about it other than that. But actually, in a quantum mechanical setting, it's quite an important matrix because it actually has some physical meaning as well. So, you know, if we consider a quantum system, which has basically just got n states, so there are n different possible states the system can be in, then the identity matrix is just a sum over the projectors to those states. And importantly, we can actually interpret that as a physical state of a quantum system. If we scale it the right way, then it has all the properties of a density matrix, or basically a classical mixture of quantum states, right? It's Hermitian, it's got a trace of unity once it's been scaled right, and it's positive. And so it's got all the properties, so it can be, it's a quantum state in this quantum system. And that has some important meaning because if we imagine we have, say, a chain of qubits, this is like the register in a quantum computer, and they're governed by some Hamiltonian. So this is the matrix which basically tells you how the system would evolve in time if you were let it evolve. And it's just some matrix. What it is irrelevant. And if we initialize these qubits in some state, which is just some point, just one of these states that I wrote down here at the top, then if our quantum register comes into the influence of some big environment or some environment, which could be some thermal noise or electronic noise or some error, or maybe our register comes into contact with like with a laser pulse, a high frequency laser pulse, which really excites it, then what's going to happen is these mechanisms are going to introduce heat into the system. They're going to excite loads of states of the system. And on a long enough time scale, the state that you will get is the identity matrix. If you heat a quantum system up continually, you will reach the identity matrix in a long time limit. And this is typically seen as a very bad thing because this basically tells you that you're typically comes with the destruction of any coherence in the quantum system. Any superposition gets destroyed, and that's exactly what you need for a quantum computer to be able to do what you want it to do. So, you know, when people try to build a quantum computer, you want to minimize the amount of noise or unwanted influences that come across. And this is because this identity matrix is not a state that you want to reach. And in the context of a series of qubits, it's because you can always write the basis, every single basis state as just a product state over the qubits. So as a state which is no entanglement between the qubits, and the identity matrix is a sum over these states. And so it also has no entanglement. And so there are no correlations between the qubits, and it's really something that you don't want. But that's not actually the full story, because what about symmetries? So in a quantum system, a symmetry is just like in a classical system, it's a quantity. It corresponds to a quantity that is conserved as you evolve it in time, and you can identify it by some operator Q, which commutes with the Hamiltonian. And importantly, a symmetry typically means that we can block diagonalize the Hamiltonian, which means we can split the Hamiltonian up into these square blocks here on the diagonal. And these blocks don't talk to each other, which means we can effectively solve the problem of our system independently within each block. And this is very important if we reconsider this heating, because we take our qubit register, but let's say we have some symmetry, which means the Hamiltonian is blocked up, and we initialize the system in that same state again, and we get some heat. So we apply some heat, maybe it's a laser pulse, but that heating actually preserves the symmetry which blocks diagonalize the Hamiltonian. Then the long time state is going to be the identity matrix, but it's only going to be the identity matrix within the block that it started in. So it's not an identity matrix over the full Hilbert space, it's an identity matrix in a subspace in the Hilbert space. And this is actually really important because that means it can have very different properties to when you don't preserve Q. And these properties will depend on the actual symmetry that you preserve and the type of symmetry that you preserve. And so in my research, I sort of looked at several crucial symmetries in quantum systems. And the first symmetry that you can get in a quantum system that's very common is something called a U1 symmetry. And really, its physical meaning is typically something like the total number of particles, the total charge, the total spin of the quantum system. And it's just a number. It's just a number representing that total charge or spin. So for our qubit register, a valid U1 symmetry might be the total spin in the Z direction. And if we heat the system up and we preserve that total spin, you can effectively prove that the number of identity matrices, so the number of subspaces in which the identity matrix possesses some correlations or entanglement between the qubits, is 0. And the number of identity matrices where there are no correlations in entanglement is L+1, which is the number of subspaces. So again, it's no good. Even if we preserve this symmetry whilst we heat the system up, the only thing that changes is that our long time state has a well-defined total spin, but that's it. It doesn't have any correlations. It doesn't have any entanglement. So it's still not a good thing. And we don't want to just preserve a U1 symmetry under heating. But that's not the only symmetry you can get in a quantum system. And another one, which is slightly more complicated, but is very important symmetry, is known as the SU2 symmetry, the special unitary group. And it typically comes in the form of 3 separate operators, which don't commute with each other, but which commute with the Hamiltonian. And so here in this qubit register, an SU2 symmetry that you can have is the total spin in each direction, in the X, Y, and the Z direction. And these operators form an SU2 algebra and effectively correspond to the fact that rotations around each of the spin axes are preserved in the system. And so if we heat the system up and we preserve this SU2 symmetry, we find something quite remarkable, actually, is that there are a large number of different subspaces, but there's a quadratic number of subspaces in which the identity matrix actually possesses correlations between the qubits and entanglement. The identity matrix in that subspace is entangled, and it's not some trivial state that is undesirable, rather than the number of uncorrelated identity matrices, which are boring and don't have any correlations, only grows linearly with the size of the system compared to quadratically for the correlated number. So there are extensively many more correlated identity matrices than uncorrelated ones. And as you go to the thermodynamic limit, this ratio will become infinite. So there are infinitely many more identity matrices, which are good than bad. And so this actually tells us that maybe heating and symmetry, heating is not such a bad thing. Maybe we can reach states that we want. And one kind of key example that I focused on in my research is that of the Hubbard model. And so this is a model of effectively a simple quantum model of electrons which hop around the lattice structure. And these electrons have 2 different spins. So they have spin up, these blue arrows here, and they have spin down, these orange arrows. And the Hamiltonian basically consists of 2 terms, one which tells you that the different spin species interact with each other when they occupy the same site, and one which tells you that this spins can hop between lattice sites. And I won't write the Hamiltonian explicitly because it's not particularly important, but this is a simple model, but it's very important in condensed matter physics because it's considered a fairly good descriptor of a number of quantum materials and the electronic properties of a number of quantum materials. But very relevant for this work is the fact that it actually has two SU2 symmetries. It effectively has a charge and a spin SU2 symmetry, the Hamiltonian, and so there are 6 operators in total that sort of specify these two SU2 symmetries. And so if we can apply some heating which preserves one or even both of these SU2 symmetries, we might see something interesting based on the arguments that I just made. And this is exactly what happens. So here, if we look at the correlation matrix, so this matrix that I've plotted in 3D here basically tells you the magnitude of the correlations between the ith site and the jth site. And this is plotted here for the ground state of the Hamiltonian for some parameters. And you can see that these correlations decay with distance as distance increases, as you go away to the anti-diagonal parts of the matrix. So this ground state is quite localized in space. The electrons are very localized. But actually, if you now heat the system, so we just heat the system up, but we preserve this charge SU2 symmetry here, something quite remarkable happens. And you effectively get this onset of order into the system. This long range order suddenly manifests itself out of the ground state. And this is just heat. There's nothing special about these dynamics other than the fact that it's heat that preserves this symmetry. So these correlations are the correlations in an identity matrix. And they're long range. So they've both been amplified and they're long range versus distance. And they're completely uniform with distance. And this uniformity with distance is known as something called off-diagonal long-range order. And it's a very important property in quantum systems because it's the fundamental property of desirable states such as superfluids and superconductors. It's sort of almost defined, well, not defining, but it's a fundamental property of them. And so it's a very desirable property to have in a quantum system. And typically when people want to engineer quantum states that they might use for some technological application, this is the kind of property that you might want to engineer. There's entanglement between the sites of the system, and there's effectively the free flow of excitation in the system. And so you can see actually the heating has given us a new pathway to engineering these kind of states that we really perhaps wouldn't expect. And another important fact is there's been a number of experiments recently where various quantum materials have been exposed to some intense laser fields, so very high frequency laser light. And it's been shown in these experiments that this laser light actually induces superconducting properties in these materials. So instead of just cooling the material down, they actually can excite it and put energy in, and they get a superconductor. And at the moment, it's very quite unknown exactly why this is happening. In such a range of materials. There are some theories, but none of them are considered, to capture the broad sense of it. And so, this mechanism of heating induced order, and I've provided some references here, provides a potential explanation for this. It tells you that, independent of any microscopic details, if you heat something up, but you preserve the right symmetry, you can expose and induce order, and specifically the kind of order that you see in a superconductor or a superfluid. And so with that, I summarize. So the conclusion really is the identity matrix isn't quite as boring as we think it is, and is actually very important and could hold some interesting properties, and that heat is capable of creating order in a quantum system despite typically being detrimental to order. Thank you.
Cool, thank you so much. So far there are no questions in the Q&A. So if anyone has any questions, you can just pop them in there. I guess I'll go ahead and ask something about the sort of experimental side, which is you have this environment that you're kind of controlling, and then you have the environment that isn't in your control. And to what extent does that need, because that in general won't preserve symmetries?
Yeah, that's a really good question, right? Because in an this is in an idealized setting where you preserve the symmetry of heat, but you're always going to have something that doesn't quite preserve the symmetry. And we don't have any particular rigorous results on this, but some smaller numerics kind of shows that, like, if the coupling between your system and the wanted heat versus the unwanted heat is large enough, then the sort of the wanted heat will basically freeze out any dynamics induced by the unwanted environment and basically allow you on some transient timescale. So instead of in the long time limit, you'll get the order you want. You'll get the order that you want on some intermediate timescale before it decays away. So there's still a window that you have if your wanted heating is strong enough, basically.
Right. Okay. Yeah, that makes sense. We do have something in Q&A, and Sam's also raised his hand, so I'll do the Q&A first. So Matthias says, where did the Hubbard model first appear?
I think it was in quite an old, I think it was in the 60s. It was a paper written by J. Hubbard. I think in order to try and describe sort of a simple model to describe the dynamics of electrons in strongly correlated materials. And it kind of, I think, yeah, it was a bit of a toy model at first, but in the last few decades, it's kind of seen a resurgence in interest because it's kind of, people can do numerics on it now and really diagonalize it for much bigger systems. And also there are a lot of experimental settings, like in ultra cold setups, where people can actually implement the Hamiltonian almost perfectly in an actual physical system. And so it's sparked a renewed interest in the model. But it's actually quite an old model, nearly over 50 years old now.
Right, okay, thank you for that. And then Sam, you had your hand raised.
Yes.
So if you just go ahead and talk.
Great. Yeah, my question was, well, I might have two questions depending on how much time there is, but the first one was these long-range correlations. Do they manifest themselves as these off-diagonal terms in the density matrix? Is that how I should be thinking about them?
Yeah, I mean, it depends. So the density matrix is still the identity matrix in a certain basis. But if you were to try to transform yourself into a basis in which, like, all the states were product states over the different sites, then they would exactly manifest themselves as off-diagonal terms in the density matrix.
Right. Right. So
yeah,
it's like these components.
Yeah, exactly. They're off-diagonal components when you look at it in the right basis.
Right. Very nice. And then, if I may, a second question was, what is this second charge that you were talking about? I think you denoted it with eta. I was very curious about what.
So the Hubbard, this wasn't known at the time, but it was known that it had a spin SU2 symmetry, which is exactly like that for qubits, total spin in the X, Y, and Z directions.
Yes.
But it was only a few decades ago, I think it was realized it actually has a second hidden SU2 symmetry, which is effectively like almost like the spin degrees of freedom. There's a second load of degrees of freedom that are analogous to spin, but they actually describe the creation and annihilation of charge. So these correlations here are actually describing the creation and annihilation of pairs of electrons at the same time. And pairs of electrons are exactly what, underpins superconductivity, is electron pairing. And so it's something that's kind of very interesting in that context. And it's almost completely analogous to the spin SU2 symmetry. It's just in a charge degree of freedom. So it's kind of harder to give it a physical interpretation, the X, Y, and Z axes, but mathematically it's analogous.
Very nice. Thanks. It's interesting.
Okay, great. So I guess we should move on then to our final speaker, who's Simone. So yeah, if you want to start sharing your screen, Simone. And he's going to speak about the role of decoherence in testing for non-classical effects of gravity. So I'll let him take it away.
All right. Is it working? Can you see it?
Yeah, looks good.
Perfect.
Yes.
Okay, it's a pleasure to talk today at the Quantum Information Society. Today we'll talk about non-classicality tests of gravity, about some recent proposals to witness non-classicality in gravity. I'll start briefly by reviewing, or asking if we really need a quantum theory for gravity. And then I will look into this proposal that have been recently studied by colleagues here in Oxford and in London, but aim at revealing some non-classicality in gravity through entanglement. I will look at some of the experimental proposals in more in detail, and I will focus on the experimental challenges that they face. So, do we need a quantum theory of gravity? I will just be very quick on this. It's not my field, but both quantum mechanics and general relativity are very successful theories. They both have robust theoretical foundations and plenty of experimental confirmations in their respective domains of applicability. And moreover, the quantum theory has proven to be the framework for the strong, weak, and the electromagnetic force. So it may seem natural to look for a unification of gravity into this framework. But at this point in time, the motivations are purely theoretical, and we have a lack of experimental evidence. And the graviton, which will be the most clear signature of the quantum nature of gravity, is far beyond the current experimental capability. So detecting a graviton would be very, very hard now. So is there an alternative way that in which we can look at the quantum nature of gravity, like discover some quantum features of gravity in an alternative way, and maybe at hopefully at low energy scales? And we can try to answer this question by considering one of the most peculiar aspects of quantum theory, which is entanglement. And we may ask ourselves, can gravity induce entanglement between two masses? So if, assuming that the gravitational interaction is mediated, which is may seem reasonable to do, can this mediator induce entanglement between two masses, here in the picture Q1 and Q2? Bose and colleagues and Marletta Medral here in Oxford have answered this question, and they said that if the mediator induces entanglement between these two masses, then it must be non-classical. Their arguments are slightly different. So Bose and colleagues use the LOCC theorem. So the theorem says that entanglement cannot be created by using local operations on the two systems or classical communications between them. So they simply claim that since if the mediator, gravitational mediator, would be capable of were capable of inducing entanglement between two masses, then this theorem would imply that the mediator must be quantum or non-classical. Marletta Medral in the 2017 paper reached the same conclusion, but in a slightly different way, making less assumptions on the nature of the mediator. They still use the quantum formalism, and in this context, they prove that if a mediator can induce entanglement between two masses, then it must have at least two non-commuting observables, which is quite a clear sign of non-classicality. In the 2020 paper, instead, like Marletta Medral, extend on this argument, and they use so-called constructive theory developed here in Oxford by David Deutsch and Chiara Marletto. And they, in this theory, this theory avoids committing to a particular dynamical model. So in this way, they can cast the problem without appealing to the quantum feature of the quantum formalism. In this context, they introduce a notion of non-classicality, and they show that a mediator using entanglement would be non-classical in the sense that they define. So even if we have slightly different arguments, all the authors reach more or less the same conclusion, which is that if a gravitational interaction is mediated and is capable of generating entanglement between two masses, then the mediator of gravity must be non-classical. So how can we test this? So Bose, Marletto, and Vedral propose the following setup to test this effect. So to test if gravity is actually capable of inducing entanglement between masses. And the setup is schematically depicted here. So they propose a sort of Mach-Zehnder-like interferometer experiment. So we have two masses, two identical masses here, undergoing each this interferometer experiment. So in some way they are put in a superposition of different spatial locations, and if gravity is actually able to induce entanglement between the two masses, then this will be probably the ideal setup to test this effect. So can we make sense of this setup? Can we try to make some prediction on what we would expect? Well, we can model approximately the setup, assuming two things. We can assume that gravity obeys the superposition principle, which means that there's a sort of branch-wise interaction. So each branch of the interferometer interacts with the other branch according to the distance that they are between them. And secondly, we can assume, since we are at low energy scales, we can assume a Newtonian-like potential. So what happens if you look at the state of a system just before the different paths gets recombined here at the location where ideally would be like something that behaves like a beam splitter? If you look at the state of the system at this point, the state of the system with these assumptions should be approximately this one. So where 0 and 1 denote the different branches of this interferometer. So we see that we have different phases appearing in front of some terms. We must note here that we have neglected the interaction between the farthest distant branches here. So we neglect that interaction because it's way weaker than the other ones. And basically, we have these phases appearing. So these phases are given by this expression. So we have, the mass of the two particles. Delta t is the time of flight, so the time they spend in the horizontal branch, in the horizontal branches. And di are the relative distances between the different branches. So remarkably, at almost all times, this is an entangled state. So this would be the ideal setup to test if gravity is actually capable of entangling these two masses. So to see if this is a feasible experiment, let's look at the scales involved. So what do we need? To have good amounts of entanglement, we need the phase that we've seen earlier, this phi, to be around 1, so to be of this order of magnitude. How can we do that? Ideally, we want quite big mass. So we have a mass here, numerator. So we want big masses and big time of flights and short distances. But now we are facing, at this point, we're facing like experimental limits, constraints, because creating superpositions of big masses is very challenging experimentally, and keeping them in a superposition for a long time is also very challenging. On this side, we could go on very low distances between the two masses, but at some point there will be short-range interactions between the masses. So specifically here in the in between these two branches, we may have like short-range interactions, like Casimir interaction between the two masses, and we don't want this to happen, because we want to be able to focus only on the gravitational-induced entanglement and neglect all the other sources that may induce entanglement, because we want to test the nature of gravity, not of the other forces. So these scales are reasonable. We're not there experimentally yet, I think, but they're not they're so unfeasible as detecting the graviton, let's say. So yeah, let's look at some of experiments, but experimental setups that have been proposed to implement this kind of experiment are ones studied by Bose and colleagues and Krishnand and colleagues. We will focus on the one of Bose and colleagues. And here is how it works approximately. So we have two copies of this thing. So we have on this side we can see what happens on a single particle. So the single particle is put in a superposition of states. It may be spin states. Maybe we can do in other ways, but usually these are taken as diamond particles with a nitrogen vacancy, and we put them in this superposition, and we apply an inhomogeneous magnetic field in this direction. This field splits the particles, so creates the branching of the particles. So we have a superposition of two different spatial locations. So one, the particle will go in this branch and in this branch. At some point, we flip the spin of the particles, and we reunite that, run them at this point. And then we can measure the particles and deduce all the properties of the system. So we do the same thing on both the particles, and we put the two interferometers, let's say, on close together. And this is schematically depicted here. And the parameters proposed by Bose and colleagues are reported here on top. So we have 10 to the minus 14 kilograms. It may be challenging. It is challenging, but so for the following reasons, because we have different levels of technical difficulties in the experiment. So both at so we have surely it's challenging to prepare the state in initial superposition, and we have to be able to control the initial state of the system. We have to cool it down, and we have to be able to create the superposition in a precise way and control the dynamics of the system when they are when it's in a superposition of two different locations. We want to be able to reunite the two branches precisely, and then measure entanglement at the end. Another important aspect to consider is the time of flight. So since these particles here are in a free fall usually, so the particles are free to fall under Earth's gravitational attraction. That means like the more they fly, the more they fall, the longer distance they will cover. So we don't want to have like incredibly tall towers so to perform experiments. So we have to keep it at a reasonable scale. Also, like as I said earlier, it's fundamental to exclude other types of interactions between the spheres, between the masses, because we want to focus purely on the entanglement induced by the gravitational interaction. Among all, we have this thing, but it's really difficult when we have big masses. Sorry, when we have a superposition of big masses, it's really challenging to keep them in a superposition. So there is this noise. So the masses interact with the environment, and basically the superposition of the masses gets ruined by this so-called decoherence mechanism. So we really want to limit this mechanism, and I'll talk about decoherence more in detail now. So what is decoherence? So as I said, when a system interacts with its environment, we can say that it transfers information to the environment. So we have a transfer of information from the system to the environment. At this point, if we don't have control over the environment, so if we can't get back this information from the environment, we lose part of the initial information of the system. what happens can be formally described in the following way. So if initially we have a product state of a system and environment, these are the density matrices of the system and environment. When we have an interaction between them, then we get in a state, correlated state. And now the statement, we don't have control over environment, basically can be described in the following way. We can say that we disregard information of information by taking the partial trace over the environment. So we end up in the following state of the system, rho S prime, which is a partial trace of the previous state over the environment. Usually what happens is the following. Here I just to see what happens for a qubit, for example, we have that the diagonal terms go usually to 1, are 1, while the off-diagonal terms go to 0, as Joseph told earlier. Like there's these terms are called coherences, and they go to 0 usually after a success and like after a sufficiently strong interaction in the environment. Yeah, so the state of the system basically goes towards a completely mixed state. And what does it mean? This means that we kind of lose the superpositions. We don't lose the superpositions. The state is even more entangled with environment, but we kind of like lose the coherences between the different states of the system. And what this means for a two-particle system, this means this results in a loss, like this destruction of entanglement. So entanglement between two systems vanishes. So this effect goes like against the entanglement induced by gravity, and so we kind of want to limit this effect. What are the main sources of the coherence? For a majority of setups that so for setups that we are considering, surely the interaction with the things around the system are very important. So in this case, we have interaction with the air molecules that surround the masses, and these molecules can scatter on the masses and interact the masses and like basically steal some part of the information from the masses. And also we have interaction with the thermal photons. So they are the photons that are in thermal equilibrium with the environment. Then they can scatter on the masses. They can get absorbed by the masses, but also the masses, since they are at a certain temperature, they will emit thermal photons and they will somehow lose information to the environment. Other sources of the coherence that we are not considering here, maybe gravitational decoherence, or it may be the decoherence induced by the so-called collapse models of quantum mechanics. So how does decoherence, environmental decoherence, affect these non-classicality tests of gravity that have been recently proposed? My colleagues and I have studied these effects, extending a work from some previous works. We have studied these effects in different setups. We, for example, here consider the setup of Bose and colleagues. So we can model the effect of the coherence on the setup. So we can model what happens in this setup as making the following assumptions. So first, we assume that the states, the initial state of our system, are the following. So it is a product state. So this is particle 1, this is particle 2. It is a product state of the two particles, and each of the particles is in a superposition of different spatial locations. So both particles are both in the left and right branches here. We assume that the particles don't deviate from these parallel downwards trajectories. So we assume that the interaction between the different branches is not enough to make considerable deviate considerably the masses from their vertical path. We assume, as I said before, that gravity obeys the superposition principle, and so we can have a branch-wise interaction. And we consider the decoherence due to the air molecules and the thermal photons. So we have scattering, and also we have absorption of photons and emissions of photons. doing some calculation, we find the following condition on the to have entanglement in the system. So we have this condition. So tau c here is the so-called coherence time, which is we can say roughly that is the time it takes for the coherence to kill the superpositions in our system, more or less. So in times in a time tau c, we have that the coherence kills the superposition, the coherences in our systems. And the condition on the coherence is then the following. So the coherence time must be greater than this characteristic time of the gravitational interaction, of this characteristic time of this particular setup, which is given by the following expression, and which is basically refers only to the parameters of the system. So we have this following neat condition of the maximum amount of the coherence that's allowed in the system. So with stronger the coherence, that means lower coherence times, we can't see any entanglement in the system. Here we have reported like the entanglement of the system in time. So measured as so this is the logarithmic negativity of a system, which is a measure of entanglement, and for different values of the coherence strength, which is this parameter here. So here we have zero decoherence, so the blue line is zero decoherence, and we reach a maximal entangled state in 25 seconds, more or less, and greater values of the coherence parameter result in lower values of entanglement in the system. How does this translate in experimental conditions? So we want to find the suitable experimental conditions to perform experiment. So this parameter gamma, the coherence, can be related can be expressed in terms of temperature of the environment and of the particle, of the masses, and pressure of the air molecules that surround the experiment. And in this figure, in this plot, we have this graph. We have plotted the environmental conditions required to observe entanglement. For example, here in the black line, we have the minimum experimental. So the conditions that allow for the observation of a minimum amount of entanglement in the system. So that means that values above this line prevent any entanglement, gravitational-induced entanglement in the setup, whilst the other lines are more demanding conditions of entanglement. But in any case, we can see that we are around 1 Kelvin, more or less, and 10 to the minus 16 pascals for the pressure of the air molecules. And the results are summarized here for some specific points. And so we have, we can see like that with 1 Kelvin and 10 to the minus 16 pascals, we reach a logarithmic negativity of 10 to the minus 1 in 1.5 seconds, sorry. And 1.5 seconds means 11 meters of like infinite free fall. Like, so a particle free falling for 1.5 seconds covers 11 meters of distance. So it may be a lot of distance, a lot of space, depending on what we have. So we may want to consider like lower amounts of entanglement. So we have shorter times and shorter distances. But then it depends on how much entanglement we can measure in the system. So yeah, what do we conclude? So we conclude like these experiments are a very promising alternative way to witness non-classical features in gravity. They require quite challenging experimental conditions and quite demanding technology to be performed. But so maybe will be feasible in the next years, but we have still to compare this with the very unfeasible task of detecting gravitons experimentally. So I think this is a great improvement over what we can do. So and also nevertheless, this technology is also crucial for our experiments. So as for example, testing the large scale limit of quantum mechanics. So we are developing, I guess we're going towards the direction, of developing the technology. and it will not be far in the future. So this kind of experiments will not be that far in the future. And the result of experiments will be very important. So if gravitation-induced entanglement is effectively actually detected in the setups, then we can claim that like gravity has some non-classical features. Nevertheless, these proposals don't hint at which would be the most suitable model for a quantum theory of gravity. So in this sense, the search, the quest for theory of gravity is still open, but we really need some experimental evidence at this point. Yeah, I would just like to thank my colleagues in Trieste and Oxford. And yeah, thank you for your attention.
Great, thank you so much. That was super interesting. Okay, so currently there are no questions in Q&A, but if anyone has any, just throw them in there. Okay, Joey has his raised hand, so you can go ahead.
I was just wondering, so far, what is the largest mass that people have been able to create a superposition of? Is there like a record for this?
So I think experimentally we can 10 to the 6 atomic mass units have been done, which is 10 to the minus 21 kilograms. Mm-hmm. And 10 to the, I remember reading a paper that says 10 to the minus 10 to the 9 atomic mass units has been proposed, but not actually done. So I think we are in the order of 10 to the minus 20 kilograms. Okay. So we are like, experimentally, we are still a little bit far. But I guess we're going there.
Yeah, it's getting there.
Yeah.
Yeah, thank you.
All right.
So you said in the next year, the experiments will be attainable.
I mean, not in next year, like, yeah, following, yeah. I don't know, maybe 5, I don't know. I'm not the expert on the experimental side. Yeah, but I think, yeah, at some point we'll far closer than detecting a graviton for sure. Like, mm-hmm. So yeah, it's in the future, not like in the remote future, like it's near future.
And is this specific to sort of the experimental setups you considered, or is it quite like general still?
Sorry, can you repeat?
As in, is this sort of so we hope that in the next, say within 5 years, we'll be able to test this out. Is this specific to sort of the what you were looking at, or is it more as in, is your framework applicable like across multiple experimental frameworks, or is it, you know, only specific to the, I think you said you looked at 2?
Yeah, look at 2. I think both 2, especially the one with Bose and others. I think that one's in next years, and also the other one looks promising. But the one with Bose is the most, like, Bose and colleagues have studied this experiment more in detail, and so we have a clear idea what we need. And I think, yeah, that is more close.
Okay.
Yeah.
Right. Sam has his hand raised, so go ahead.
Yeah, so I was just wondering, the experiment is a way of distinguishing between theories of physics in which gravity is classical and in which it's quantum. What do you think is going to be the case? How do you think it's going to turn out?
Oh, good question. I don't know. So my gut feeling is that we are able to, I don't know, probably we are able to, I don't know, that's a really good question. I think my feeling is like that we are, so the whole point here maybe would be like, does it like obey the superposition principle, so gravity? So if you have a superposition, what happens to, how is the gravitational interaction on the other side? So does it look, it may be reasonable to assume that each branch has exerts a different gravitational interaction on the other mass depending on which branch, on which position they are. So I don't know. So my feeling is that they will induce entanglement. So maybe gravity will show this kind of non-classicality. Yeah.
Very nice. Thanks.
Okay, thank you so much to all three of you for speaking. It was great to have sort of a diverse range of speakers, I think. I found it super interesting. So next week, we're going to have Earl Campbell, who is a researcher at AWS, Centre for Quantum Computing, and he's also a senior lecturer at the University of Sheffield. And he's going to be speaking about fault-tolerant quantum computing in biased noise architectures. So yeah, that's going to be next week, Thursday. But yeah, otherwise, I hope everyone has a great evening. Yeah, and I'll let you go now. Thanks again.
Thanks so much for having us.
Thank you. Yeah, thanks for having me.